Hello and welcome to today's live webinar. We will be talking about laser as a highly productive and flexible tool. We are happy that so many of you have registered for today's webinar and are also now joining us live. Of course, we want to give you the best experience and meet your expectation as good as possible. And in order to improve that, you have the possibility to give us questions live during the webinar, either using the chat function, the live chat, or you can also just use the anonymous question function, which is available. My name is Konrad Eibe. I've been working with EMAG for over 20 years now, 9 years in technical sales, and since about 2 years I'm the head of offer engineering here at EMAG Lasertech. Yeah, you can see it, you can maybe also hear it. We are not sending out of the studio today, but we are sending from EMAG Heubach plant. We are located about 60 kilometers east of Stuttgart and half an hour in the car from EMAG headquarters in Saalach. Here in Heubach, we are the technology company within the EMAG group for ECM, meaning electrochemical machining, and what we will be talking about today, laser technologies, meaning EMAG Lasertech. Today we will be talking about the following. First of all, we'll be given an overview of the EMAG Lasertech machine portfolio and look in detail at the ELC6 machine. Then, since we are here live in the plant, we will talk about the newly designed new setup of the Laser Application Center here and also give a live tour. And here we will also see some of the machines out of the machine portfolio in action. When we then come back to the presentation, I will try to close the gap or close the circle to show how we use the machines and the technologies, which we also see in the center, to produce and deliver full turnkey systems for our customers. Last topic will then be the laser hardening technology with the example of our ELC 1300 LH machine. This is an overview of our ELC machines. ELC stands for EMAG Laser Center. The number behind it gives an indication of the workpiece dimensions. The letter then, as is normal for all the EMAG machines, gives an indication either of the machine design or the technology which can be used. Let's start on the left side. These are our universal machines, meaning they are more flexible. The machines on the right side are more component specific. I say more, why? Because the distance is fluent. Of course, these machines on the right side can also be used for different applications whenever it fits. So whenever an inquiry comes, we will of course check the whole portfolio, what is possible, and try to find the best fitting solution. The ELC 160. This is our most common machine. Almost 200 of these machines are producing parts around the globe. It was designed for a welding diameter of about 160 millimeters, but over the year that was more and more expanded. However, the name was established and stayed on. The machine is a linear design. There's a working spindle with a clamping device coming from the bottom, and that is moving through the stations linear. In 2018 then, we introduced the ELC6 to the market. The main difference, this machine is not a linear design, but it has a dial table for loading and unloading. That means, of course, that the load-unload can do in parallel to the production time. And the cycle time will in that way be, of course, shorter. Now, this machine has, in the short time since it's been on the market, already become our most important machine, and this is why we will look at the machine in detail later. Now, these two machines are used typically for passenger car powertrain components. Now, the ELC 600 machine is right between universal and specific. The reason for this is it's a bigger machine, so the components are more or less out of the commercial vehicle powertrain spectrum. The machine itself is very flexible, so if the application is right, we can use this machine, of course, outside of these workpieces. But for now, it has mostly been used for truck differentials. The ELC 1200V machine is also a dial table machine. We'll also see it in the Laser Application Center in a minute. This machine is also quite flexible. However, the main application so far has been welding of aluminum tubes to fittings, for example, in air conditions of passenger cars. However, when there's a simple weld application, this machine might be the right choice. And then on the right side, before mentioned, ELC 1300LH. This machine is for laser hardening, and workpieces of up to 1300 millimeters in length can be hardened. We see on the bottom what it's mostly used for: laser hardening of HSK tool holders. So these are the, let's say, the main machines, the main process machines, the ELC machines. We also have machines for other processes. This is the laser cleaning and the ultrasonic testing. They are usually used in the process chain in a fully automated and linked system. However, all these machines are also available as standalone. Now, the LC4 by its size is also defined for, let's say, passenger car powertrain workpieces are perfect. LC8 again is a bit bigger. This one will then be mostly used for commercial vehicle powertrain parts. And then we come to the ultrasonic test machine. This is then again for passenger car powertrain workpieces. Now, this was a machine overview, and now we'll be looking in detail at the ELC6 machine. Again, the ELC6 machine has quickly developed to be our most important machine. We see here the two views. One is from the operator side, the other one is from the loading side. In this version, and that is in most cases used for automated loading, but it can also be delivered as a standalone version for manual loading, as shown here, then with a safety partly safety fence and a light curtain. This is the machine design. The view now open from the operator side. So position 1, the loading area, is not visible. That's behind on the other side. But position 2, the swivel table, the dial table, then brings the workpiece from the loading area into the weld station. Position 3 is then the working spindle coming from the bottom that clamps and locates the part and then brings it up to position 4, which is the counterbearing. The counterbearing holds the upper weld tooling. And the spindle, position 3, from the bottom brings the axial force into the workpiece. Number 5 is the welding head. The welding head has certain positioning axes. For example, a horizontal, a vertical, and a swivel axis can be integrated, and that is what gives the machine its flexibility. Position 6 is then the supply units, for example, the electrical cabinet. The position of this is, of course, flexible wherever it is needed in the plant. Yeah, the machine is fast, loading and unloading in parallel. It's flexible, different weld toolings can be installed, and the weld head is again mounted on different positioning axes. It is precise because in this machine, like in all our ELC machines, we use our own customized clamping devices. These are completely designed, manufactured, assembled here in Heubach as well. So this is truly an EMAG product. The process safety comes from measures such as the active control of the welding position, or for example the use of state-of-the-art process monitoring systems like an LWM, a laser welding monitor. The machine also brings economical advantages. Why? Laser is of course a very efficient tool when it comes to energy input, and in the machine we are using preferably electric drives instead of pneumatic or hydraulic units. Last but not least, the machine was designed to be very compact with the flexible positioning of the extra supply units so that we can find the best fit inside the customer plant. The Laser Application Center. I am right now standing, let's say, on the bottom in the middle of the Laser Application Center here in Heubach, and we wanted to use the chance to present it to you, give a live tour of this and show the equipment and the expertise we have here. First up, on the right side, to my right, there are machines out of the upcoming brake disc coating technology, the ERC 450 Duo LMD for laser cladding, and the VRC 450 DG for grinding. And here I want to mention that around the middle of April, there will be a separate webinar for these technologies. Then to my right, we see the machines, the ERC 1200V, an ERC 160, also an ERC 6 machine. However, that is just arrived a couple of weeks ago and is not set up yet completely. And we have the ultrasonic test. And now I want to use the chance and we start the tour. First, we visit the ERC 1200V. As mentioned before, a dial table design, very quick cycle times. So the aluminum tubes we saw earlier, those reach a cycle time of 6 to 8 seconds. But again, the machine is very flexible, and that is also the reason why here in the lab we are right now using it for the laser cleaning technology even. So what we have is installed in the working area is the scanner head. This has a working area of 85 by 85 millimeters. You can also see the scanner head is mounted on 3 NC axes. So also here great flexibility. The laser source which we are using is an IPG 200 watt laser source with 1 millijoule of peak power. And we can now show you a live example of a laser cleaning process. The total workpiece has been blacked with a black marker. And now we want to see how the laser removes the black paint, yeah. So first the cleaning head moves into position. The workpiece rotates, the power is on, and the paint is removed. Wow! Here we see the result now. On the left side it's been cleaned and the right side is still black. Thank you, Siggy. And just to give a peek into the next chapter, we can see here the EC scan software which is used to control the process. I want to say here EC stands for EMAG controlled. So this is a software which is an EMAG product, so we developed it and we do the maintenance for it as well. So it is completely in our hand. Now we come to the ELC 160 machine. This machine in our lab is used for most welding tests. We see here the setup. It's a laser head with a 1:1 to 1.5 ratio. That means a fiber diameter of 200 microns will lead to a laser spot of 300 microns on the workpiece surface. And of course, we have the possibility to use different technologies, such as, for example, the bright line weld technology. Right now installed on the other side machine is a different optic configuration. It's a scanner of the PFO type. PFO stands for Programmable Focusing Optics. And it is set up right now for a laser hardening process. And this we can also now demonstrate live. The workpiece is rotating. The laser energy on the surface brings the material into the desired austenite structure. And then the material itself puts away the heat from the surface, and in that way quenches it and brings it to the intended martensite structure, which gives then the required hardness. So now we have just changed the surface and reached the required hardness. Thank you, Stefan. In the meantime, I have received a question. This goes back to the laser cleaning. The question is, what is the effort of the retooling of cleaning machines? Keyword flexibility. So on the cleaning machines, we usually use some simple fixtures to position the parts. We have 2x2 fixtures, usually 2 in the front, 2 on each side of the table. So each 180 degrees. And those are equipped usually with quick change interfaces. So it's a matter of a couple of minutes, maybe 5 minutes, to exchange those fixtures to, let's say, from a shaft to a differential. Then another question was, what about deep soiling or rust? Can this also be removed with laser? In general, yes. However, there will of course be a physical limit as to the depth of the rust, which can be removed for sure. If there's an application, we will gladly look at it in our lab. We have the equipment here and can easily run some tests. Okay, so for laser welding, a typical process chain is laser cleaning, laser welding, and then the ultrasonic test, to have a non-destructive check if the weld is okay. And we see here the ultrasonic test machine setup. The part is rotating and the probe is in the middle inside the workpiece and fixed. The probe is actually inside a plastic nozzle to supply some water. Why? Because the ultrasonic test signal cannot travel through air. It needs to have either a solid material or a liquid. So between the sensor and the metal you need water. So this check is being done, and the evaluation you will see then on the screen. I also mentioned here, it's the EC Sonic software. Same approach as for cleaning. EC is for EMAG controlled. This is our own software. Now you see a result. The red line presents the limit from which a fault is defined. So everything about the red line is defined as a fault. In this case, 2 defects have been counted, 5 are the limit, the part is okay. Single defect was maximum 5.87 allowed. We have just below 5.84, so okay. And the sum of defects can be up to 17%. In this case, only 11, so okay rated. Now we have a question coming back to laser hardening. What are the advantages of laser hardening? I will come back to this question later in the webinar, actually. Is an induction hardening much faster and more flexible? Much faster, I would not say that it is. So induction hardening, if you want to harden a complete shaft over the complete length, probably induction hardening is faster and the more economic solution. However, induction hardening is definitely not more flexible. Why? You need induction coils. Those are fixed. And with the laser, you are very flexible. You can move the laser beam wherever you need it and with the intensity that you need. So laser hardening is definitely more flexible. And what hardening depth can be achieved? Everything between around 0.2 and 0.8 millimeters, or even up to over 1 millimeter can be achieved. However, of course, we have to keep in mind that there are certain physical limits, of course, but in general, up to 1 millimeter can be reached. Okay, so now we have seen the non-destructive testing of a weld seam. However, if you want to be sure, at some point you also have to cut some parts and really look, let's say, inside the weld seam. This is what we do in our cutting, etching and microscoping laboratories. It's 2 rooms. This room here is used for first off cutting, meaning cutting slices or segments out of the workpiece, of course across or through the weld area that you want to look at. Then we go to polishing, where different grades of grinding paper are used to polish the workpiece surface. And last but not least, we come to the etching that is needed to have a clear visibility of the part later under the microscope. For example, Nittal is used for usual steel, and etching according to Adler is used, for example, for stainless steel. So cut, polish, etch is here. Then we move over to the other room. Here are the microscopes and the hardness testers. First of all, we want to point out this is our newest microscope. It's really state-of-the-art, newest technology being used. Has a magnification of up to 2000. You can really look in detail at the microstructure and really analyze the material. In this case, it is a coating layer of laser cladding. And also it's a so-called LIPS function, which is a fluorescence method to analyze the material within a workpiece. Of course, other more, let's say, traditional microscopes are available for video analysis, or in this case, simple optical checks on a stereo microscope. Over to that side. For sure, in laser hardening or laser coating, which points towards or which has the goal to give a hardened surface, we have to do the hardness check according to Vickers or Rockwell, for sure. But also when you have a weld seam, you make certain hardness measurements across the weld seam to check the hardness in the heat-affected zone. So this is being done here. And here's another more simple, more flexible hardness tester as well. I have received another question. Let's step outside quickly. The question is right here: can the ultrasonic inspection be used for checking brake discs? For checking coatings, for example, brake disc coatings. Now, the method we are using in general, I would say not. Why? Because we use the ultrasonic check to measure a weld seam that is 4 millimeters deep, for example. So we go into the depth and we want to look from the side onto this weld seam in the depth. So it is quite possible that you can also do this on a surface level, but you would have to cover a lot more surface. So in my opinion, no, but however, I can take this question on and try to give an answer maybe later in the chat. Oh, exactly, right. So let's move on quickly to the ELC6 machine. Like I said before, this is not up and running yet perfectly. However, I wanted to use the chance to show you. The machine has best possible accessibility. I'm literally standing inside the machine, right at where the process is at. So maintenance activities, changeover or setup of new workpieces, very easily. The operators will be very happy. And then we see the components which we mentioned before. On the bottom, of course, the working spindle with the clamping and locating, which brings the workpieces up to the counter bearings. We see the two different types that can be installed. So this would be workpiece group 1, this would be workpiece group 2, and we can do an automatic changeover. As you can see, that whole thing is a slide unit. So whatever tooling is needed at the moment is used. And then we have here, for further flexibility, the weld head is mounted on different axes. We see the vertical axis, we see the horizontal axis, and also the swivel axis right here, which gives the flexibility. Okay. In the meantime, another question regarding tests or prototypings we can do in the laboratory came through. How much effort is required for process reliability? And is this laboratory equipment necessary for every customer in order to achieve good welding results with laser welding? So, how much effort is required for process reliability? If a process has already been defined and developed by the customer, for example, and we only need to do process validation, that is a matter of only a few days. The lead time for that would be, depending on what tooling is required, 2, maybe even to 6 weeks beforehand. However, if you intend to do a complete process development, that will take up some more times. I would calculate with maybe 2 weeks as a rough value, and the lead time will then start maybe at 4 weeks and go up to 8. And then, is this laboratory equipment necessary for every customer in order to achieve good welding results with laser welding? Yes, at some point you have to do those cuts, you have to look on the microscope. So if you want to run a laser welding process, this is mandatory. Okay. So now, summing up the tour real quick of the Laser Application Center, I want to point out that we have given it a new look, but that's not the main point here. The main point is, as you can see on all this equipment and all those machines, a lot of investment has been done in the last years, and we really have a lot of capability here to support the customer products. And for that, we have 8 highly qualified colleagues working in the department who will develop the process, improve the processes, and most important, bring them to a point where they can be used for the customers in the production. So with this technology explanation, I want to build the bridge. Like I said earlier, machines, processes, these are two key components of full turnkey systems, meaning automated systems that link 5 or even up to 10 processes fully automatic. For this, we will look at two examples which we have built. First one is out of the electric drive of a passenger car. It's a rotor shaft. It's a two-piece design. On the bottom you see the process chain, first the laser cleaning in an LC4 machine, and then the ELC6 is used for assembly, induction preheating, the seam tracking and position correction, and the laser welding. So all of this happens in the machine in this case. System looks like this. We have load unload on the left side, then the LC4 and the ELC6 machine. We bring in the parts, first laser cleaning, laser welding with all these sub-processes, and then back to the start. For this we have also a short video. The two single components are on the left side, the finished welded is on the right side. Single components are picked up, brought to the laser cleaning LC4. We go into the laser cleaning area. First up, the weld area of the first component, then over to the second component. Then out of the machine, and the gantry brings it to the ELC6. First off, the last welded part goes out and the single components come in. Of course, on the other side, a part is welded at the same time. Now we go into the working area, and there we already have to look quick because the joining process, the pressing process is really quick. It's already done. And then we preheat the part because of the high carbon content. So now we have length tolerances and we have also heated the part. So now it's very important to do a seam position control. We are using the EMAG easy seam system to tell the weld head exactly what to do or how to position during the welding. Now it has been finished, and then the workpiece is unloaded. Of course, new components come in, and the finished part goes back to the pallet. Second example, this was a system which is used for two workpiece groups, even differential and intermediate shafts. Both those components come also out of an electric drive of a passenger car. And this is usually this couple we see, intermediate shaft, differential. And we have a system which is able to weld both those parts with very, very little changeover. We see here even more processes, laser cleaning, the joining outside of the machine. Then we have a run-out test, the laser welding in the ALC6. Then we brush the surface, go to the ultrasonic test, and if the part is okay, do the laser marking and then the unloading. So first of all, after load unload, we go to a DMC check. Then comes the laser cleaning, followed by the press process. We go up to the run-out test, then down to the ELC6 machine, where we do the welding. Then the brush station for the surface, ultrasonic test, and on a okay result, we go through laser marking and to the unloading. For this we have a video of a very similar system. An intermediate shaft. Single components come in. The DMC is being checked. And now the parts are taken from the pallet and to the laser cleaning machine. Again, it's a LC4 design. And we do the laser cleaning. So I have now received another question. Why do the parts still need to be cleaned before welding? They already come clean from pre-machining. That is not necessarily true, because there might still, from the pre-machining, there might be still some residuals, for example, from coolants or other fluids on the part. And if you have those organic substances on the part, then that's a high risk for cracking of the weld seam later. So that is definitely recommended, and let's say, for example, in differential welding, 90% of inquiries have this specification that laser cleaning must be done. Okay, the cleaned part has already been pressed together. Now, before the welding process, also here, because of the high carbon content, preheating is being done of the weld area. This is also to improve the weld quality and reduce the risk of cracking. The hot part then goes into the laser welder, in this case an ELC 160 machine. We see it on the linear slide. The spindle brings the part into the upper weld tooling. You don't see much, and that is okay, because everything is covered. We have an inside and outside cover. Only the weld area is free. And on the lower right, you see the process monitoring with a laser welding monitor, LWM in this case. The welded part then is flipped over and goes to the brush. Part rotates and brush rotates. Then we quickly go back onto the pallet and into the ultrasonic test station. So first the part is pressed down against the spring load to have it aligned correctly in the gripper, and then we do the ultrasonic test. Again, here the probe is inside the workpiece and the water is flowing, so this bit of water also needs to be dried off. This is done with rotating the part and in addition with some blow air. And then the finished part goes to the unloading area. Okay, so now we have seen full turnkey systems. What makes EMAG LaserTech turnkey systems special? Simple, everything is delivered out of one hand. So the machine tools are of course our product, but also the custom clamping equipment and the automation is completely done by us. Everything from design, assembly, even manufacturing and up to startup, everything comes out of EMAG. And last but not least, to really make us here also a technology partner, the processes, which we saw first of all in the Laser Application Center, but also the supporting behind this, the EC application, the EMAG control application, which really make the software our product. And here is a list of these EC applications which really give the customer the benefit. First off is EC seam. In this case, we saw it earlier. Now we can look at it more in detail. A laser line is projected across the weld area. The camera which is located in the back of the weld head detects this laser line and also the gap where the laser line changes, and this is then the position that we need during the welding right after that. So I will go first forward one slide. The first step is the measuring cycle. So up to 20 points can be measured. The second step is then, of course, the calculation. And the third step is then what the weld head does during the weld process. And now I'll go back one slide. There are two different possibilities. You can either use a complete control function where the weld head really follows the path during the rotation of the workpiece, or the other possibility is the seam position correction. So one correction value is chosen before the weld head moves to this and then stays fixed during the weld process. Both is easily possible. The second application we already saw out in the center, ultrasonic testing, and the operating software for this is the EasySonic. Again, completely our product, no third parties, no suppliers or sub-suppliers involved. What do we see here? The B-scan. The B-scan gives an indication of one track that has been measured by the ultrasonic test, and of course the colors give then an indication where on this track faults have been detected. Again, the faults are everything that is above the red line, which is the gate that needs to be defined during the process development. And here you see in the amplitude chart, you also see the red line, the gate, and the peaks that are above it. And again, to view here a bit better on this chart, which we have chosen, 3 defects were over the red line. The limit is 5. The biggest single defect was 1.2 millimeters, 1.2%. 2% are allowed, and the sum of all detected defects is 2.3, and 5 is allowed. So 3 times okay result. And the good news is, with this software, it's easy to adjust these limits. For example, if you see we have to look closer at, for example, the single defects, or we have to look closer because we have this and that weld situation. We have to look closer at the number of total of the sum of all the defects. Then it can be easily adjusted in the software. Same goes for the Easy Join, which is a software tool for press process control. Of course, in a press process, the force and the path need to be monitored, and then the real curve which occurs during the process is recorded, and this curve has to pass through a certain window, meaning a rectangular shape, in the chart in order to be rated OK. And why we have this display here is also to be shown. You see the workpiece IDs here, so you can store each curve, each process data in the control unit. And to organize all this data, all this process data, the tool we use for that is our Easy Data. Now this is first the process view in the Easy Data software. Here you chose what process you are looking at. You see all the different workpieces, and then in the data display you see what position this part was cleaned in, for example, and what power was used. And also in the Easy Data available is then the workpiece view. Here your search function is after a workpiece, then you find a certain workpiece, you see an overview of all the process parameters, and for example you can also then switch between different process plans, meaning different batches or even different workpiece groups. Okay, now we want to give a closer look into the laser hardening technology. We see it here. We chose some sample workpieces to show it. It's a surface hardening technology, and it's very flexible. I mentioned this before. We can, for example, harden some inside shapes or some grooves like that. And if a workpiece changes, we don't have to exchange, for example, a do a changeover of an induction coil, we can just give the laser a new position. The machine which we are using for this is the ERC 1300LH machine, which is shown here. It was used for this example for those HSK tool holders. Hardening depth was between 0.6 and 0.7 millimeters. And you can see on the machine also here a huge front door, very well accessible. The operator is standing inside the machine literally. We see here again the PFO, the programmable focusing optics, which is the weld head, let's say, and it is mounted even on 4 NC axes to give it a perfect flexibility. This is again the view now with all the extra supply units, and of course on the right side the laser source, and the fume extractions can be positioned where it is necessary or where it makes the most sense in the customer plant. Coming back quickly to the laser hardening process itself, what happens? Again, we move a laser beam across the workpiece surface. You see the feed direction here, and rectangular to the feed direction, the laser energy is scanned back and forth. That way a track of a width of 10 to 30 millimeters is being hardened. So the heat we put into the workpiece leads to the structure of the material changing to austenite. This is just like in the normal hardening process. Now what is different? The workpiece itself is cooling down, and that cooling is enough to do the quenching. So after this cooling down, you immediately reach the intended hardened surface, meaning a martensite structure. Typical values are, like we said earlier, 0.4 to 1 millimeter is possible maximum, and up to 60 Rockwell can be reached. Okay, here's a question coming back to our easy seam, meaning our weld seam position control. Does it have a negative effect on the process time, or does the system run parallel to the main time? Now, the measuring run, meaning the first step which is being done, that has to be done before the weld. So that will take about 2-3 seconds depending on the workpiece parameter, workpiece diameter. However, the process itself then, meaning the tracking during the weld and also the calculation, that does not influence the cycle time. And last but not least, the advantages of the hardening process. First of all, I want to say the material is self-quenching, so no cooling media is required. And that also means that the machine, for example, our laser hardening machine, can be integrated perfectly in a, let's say, normal production line. There is no salt bath or something like that, no additional medium. That is a perfect fit to a production line, and that means in most cases no separate discharge for the hardening process will be necessary. And then, of course, it's a very precise input of the energy, only where you need it, only where it's needed. So very good economy. Then the quality, like I said before, thanks to the CNC technology and the laser scanner, it's very precise. The repeat accuracy is very good. And because of those reasons, of course, the distortion is low, so little to no rework will be necessary, and also the hardening stress, of course, is low. And then the flexibility, the variability, the hardening of especially, this is possible, this edge can be hardened, this is right next to it, but it's not hardened, so that's very easily possible with the tool of the laser. So, a quick summary of what I talked about the last 45 minutes. First, we gave an overview of the machine portfolio, in special the ESC6 machine. We saw then those machines in the laser application center. We saw the new setup, and we saw what makes the EMAG LaserTech turnkey systems special. Everything is out of one hand for the customer. There's one partner to talk to. We can go deep into the technologies if needed, and that is the true support and the true customer benefit. Last, we looked also at the laser hardening technology and what advantages it can bring. Okay, so we hope we gave a good overview of the laser as a tool. We hope the questions were answered that you had. Thank you very much for your attention, and greetings from Heubach.